Okay, so we're on section 7.3. We got number 5 tells us that we have the solid between planes perpendicular to the x-axis between x equals -1 and 1. And the cross-sections perpendicular to the x-axis between these planes are squares whose bases run from the semicircle. And so if we draw the base here, we have 1 minus x squared and negative, radical 1 minus x squared and negative radical 1 minus x squared. So ultimately, the y equals radical 1 minus x squared would be that function. Okay, so ultimately, it'd be just a circle here, and let's see. Actually, it goes both directions, I guess. We're going from -1 to 1. It says. And then the bottom half would be the negative version of that same thing, so ultimately we'd have just a straight up circle here. So, and again, split up into two parts would be those two equations individually. If we were to draw them with our calculator, we'd have to draw both parts to get the whole circle there. Alright, so keeping in mind that being our region, and it says that the solid lies between planes perpendicular to the x-axis, blah, blah, blah. The cross-sections are perpendicular to the x-axis between these planes, and they are squares. Okay, and so again, perpendicular to the x-axis means that they're going to be vertical slices here. And if these are going to be squares with the base in the plane, that means that they're going to come out of the plane at us, if you will. So, and again, it's difficult to draw in 3 dimensions, but ultimately we're getting that situation similar to what we had yesterday at the beginning. Okay, so if we draw a slice, it's going to come out of the paper at us, if you will, as a square. And so in general, though, remember what we want to do is write down the general formula for the shape itself, which is a square, and then see if we can come up with an expression in x that gives us the area of said square. So bottom line here is what would this side length be here if I went from this point to this point? Would it be that far up and then that far down? It's subtraction of those two, if you will. So really it would be 2 and then 1 minus x squared, all squared. True? And so if we have that as our integrand ultimately would be 4 times 1 minus x squared. 2 would be a 4, and the square root would cancel the square. And then if we write an integral from -1 to 1, then that should sum up all the squares then, shouldn't it? So if we do that, once we write the integral, it's a matter of calculator problem. Oh, it does say analytic. You're right. So, alright, so analytically we'd rewrite this as 4 minus 4x squared, I guess. And antiderivative of them would be 4x cubed over 3. -1 and 1. So the 4 in there, or the 1 in there would give us 4 minus 4 thirds. And then the -1 in there would give us -4 plus 4 thirds. Putting a 1 in there, 4 minus 4 thirds, -4, -1 in here would give us negative, this would be plus. So ultimately 4 would be 12 thirds, so we'd get 8 thirds out of that parentheses. And out of this parentheses we'd have -8 thirds. And ultimately it'd be minus again would give us our 16 thirds. That would do it. Questions on any part of that one? What else? 7. And 7, we have the drawings partly done for us there. It says we have, we're looking at the curve y equals 2 radical sine x is our base. Is going to be solid that's in this region from 0 to pi on the x-axis. Cross sections perpendicular to the x-axis. And part A says they're equilateral triangles with the bases running from the x-axis to the curve, etc. So ultimately, the picture that they have shown there, keep in mind that's an equilateral triangle, comes out of the paper at us, and again, their drawing is obviously better than mine because they can have better technology to draw than I have bad art. So, bottom line is here, just like we did yesterday with the equilateral triangle, we need to figure out what is the formula for that one equilateral triangle. Well, we know in general that any triangle is 1/2 times base times height. In this case, our base could be the region here in the plane, which is ultimately the function. And then the issue is, can we find an expression for the height? Well, like I showed you yesterday, if we take that equilateral triangle and we split it into two parts, we make a couple of right triangles. Ultimately, that would be radical sine x, radical sine x. The whole base was 2 radical sine x. And I know that this is also now a 30, 60, 90 triangle. And we said yesterday, our relationship between short side and long side, because the long side is the height that we're after. If we multiply the short side by radical 3, we get the long side. So if I do radical sine x times radical 3, I'd get radical 3 sine x, and that would ultimately be my height. Questions on getting the height for that particular triangle? Alright, and once we have the expression written for our height of the general triangle, then we can sum that up by writing an integral. We're going to write an integral on 0 to pi. And if we simplify this stuff here, we're going to get 1 here. If I do the square root of these two multiplied, I'd have 3 sine squared x. So ultimately, wouldn't that be sine x radical 3 dx? The sine squared would come out. Square root of sine squared of sine. Radical 3 would still be in there. I'd factor the radical 3 right out of there then at that point. So we got radical 3, 0 to pi, sine x dx. Antiderivative of sine x would be negative cosine x. On 0 to pi, cosine of pi is negative 1. And cosine of 0 is 1. So in working all that, we get 1 plus 1, 2 in the parentheses. So ultimately, we should get 2 radical 3. Alright. Questions on any part of that one, the equilateral triangle? Alright. And how would that change then for part B if we had to do this with squares with bases running from the same? Ultimately, if we did that with our squares, our general formula would just be a equals s squared. Remember, the side length would just be the function, wouldn't it? So wouldn't that be the side length? So it would be 4 sine x would be our integrand on negative 1 to 1. So I'll let you do the integral part of that one. We got the setup part. What else?
Wait, why is it negative 1 to 1?
I don't know, because I'm still on the last problem. Mike?
Number 9.
Alrighty, number 9, we got, so it's here that solid lies between planes perpendicular to the y-axis, where y is from 0 to 2. Cross sections perpendicular to the y-axis are circular discs with diameters running from the y-axis to the parabola. And so ultimately in our picture here, if we're going to do the parabola, radical 5y squared, and we can see that 0, 0 is clearly a point. And if we pick some other values for y here, like say for instance, it really doesn't matter what we pick here, I guess we could pick anything here. If we just picked 1 for y, our 1 would be radical 5, and negative 1 would also be radical 5. Okay. So if we did radical 5, 1, radical 5 being 2 and some change, so 2.21 and 2.2 negative 1. And we're going from y equals 0 to 2. So ultimately our 2's here would give us 4 radical 5. So 4 radical 5 is going to be how many? So 8.9, almost 9. So if we come out to 1, 2, 3, 4, 5, 6, 7, 8, 9. So almost 9 and up to 2. Down to negative 2. So ultimately, again, we have sideways parabola going all the way out to y equals 2, if you will, which corresponds to x equals 4 radical 5. Okay. All right. So ultimately, that's our our region. And in our solid that we have here, it says the cross sections are perpendicular to the y-axis. So ultimately, we're looking at horizontal cross section this time. Okay. And it says these cross sections are circular discs, okay, with diameters running from the y-axis, okay, to the parabola. And actually, I have this backwards. So actually, we're going from the y-axis to the parabola, so we're actually looking at that and that. So the region is not this stuff. The region is actually this. Again, it says these discs are running from the parabola to the y-axis. Okay. So the region in question, remember, think about it if we flipped it like this. Okay. The region between the curve and the x-axis would be what I have shaded now, not the stuff in the middle. True? Okay. So that's the region in question, the shaded region, not the inside stuff. So this is actually not the disk, it'll be that, let's say. So if that's our slice, and we go circular disc, if you will, something like that, and coming out and going in, coming out of the paper halfway, going back in the other way. Okay. So down into the paper, up out of the paper. And from there, again, we start out with just our general formula. We know that the area of that circle is pi r squared. Okay? So start out with, we know the shape is a circle, so we'll start out with the general formula for a circle. And then the issue is, can we write an expression here for the radius of this circle? Okay? Now keep in mind with this circle, the radius is going to be from essentially here to here. True? Okay. So the question is, what is that right there from there to there? Well, what would it be from y-axis to curve? From y-axis to curve, it would be that, wouldn't it? Okay. So ultimately, from y-axis to that point, what would it be of this? It'd be half of that, wouldn't it? So that radius right there is half of radical 5 y squared. Okay. All right. So that radius, again, for that circle that we have drawn is from here to here. That would be halfway to the curve itself. And to the curve itself would just be this x value, okay, which is radical 5 y squared. And again, we want to write it in y because we have a horizontal slice, if you will. And so from there, we'd have ultimately squaring that stuff. We'd have 5 pi over 4 y to the 4th as our area formula for that circle. So half squared is quarter. Radical 5 squared is 5. Y squared is y to the 4th. And so that ultimately would give us our area of one circle. And so how do we find the area of all the circles? We write an integral from negative 2 to 2. And why negative 2 to 2? Because we're going in the y direction because we have a horizontal slice. Okay. So the y values go from negative 2 up to positive 2. True? And each of those circles then is going to have our area of that. And so from there, if we do our 5 pi over 4, we'll take that out. And do our antiderivative. Y to the 5th over 5. And if we put 2 in there, we're going to get 32 fifths minus negative 32 fifths. So it'll be 5 pi over 4 times 64 fifths. 5's would cancel out. 4 and 64 would cancel out, which gives 16 pi. Right?
Wait, how come if you do it like the area and side of the curve, you put the same dimension?
inside?
Inside the parabola.
Um,
Or is that just like,
I mean, what did you write? You found the area of the inside part?
yeah.
So what did you use for your radius then?
Oh no, wait, I got 8 pi. So I did square root of 5y squared over 2.
So I'm not sure what the question is.
Wait, never mind. I thought it was the same answer, but I got 8 pi.
Yeah, ultimately, had it been in this region here, remember the radius of this circle here with that as the slice would have had to been, first of all, would have had to been this 4 radical 5 minus the function to get the distance between those two, and then half of that. So that would have been a little bit more complicated of a deal because we had more radicals to work with. And ultimately, it might not have been terribly difficult to find the answer. But again, keep in mind though that the giveaway here is that it says
No,
we're
I
using.
did the same thing.
So what?
What's your question?
I don't know, I'm confused.
We can tell.
Josh?
Like, I did it.
The book says it's 8 pi.
Yeah, nice.
Did we miss a square somewhere then? Because maybe we missed a. Because this is our pi r squared, and if this is our circle, then it said the diameter runs from the y-axis to the curve, right?
Yeah.
That's what it says.
Number 9.
So the radius would be halfway to the curve, which would be half of that quarter.
Take it from 0 to 2. That's why. Not think. So the y-axis at y equals 0.
Oh, it says 0 to 2.
So
Okay.
same thing minus half.
So basically, this whole half of it is not even part of the whole operation. It's 0 to 2. That's why the problem is. So if we change that to 0 to 2, 0 to 2, we'd ultimately gotten 0 for that. So this would have been 32 fifths. So that's how they got the 8 pi. All right. I thought it was the whole entire parabola, but it's actually only half the parabola, just the top half. So our slice that we drew should have actually been up here in this part, in the upper part, from 0 to 2 only. All right. What else? Scott?
8.
On 8, we have perpendicular to the x-axis between negative pi over 3 and pi over 3. And the circular disk says from the curve tangent x to the curve secant x. So ultimately, again, we're going from pi over 3 to negative pi over 3 to pi over 3. Keeping in mind that for both of those functions, it has asymptotes at pi over 2, negative pi over 2. We know that the tangent function, negative pi over 3 to pi over 3, would look essentially something like that. The secant function is positive in that area. Remember, that goes down to 1, so it might have something like that. And again, you can verify that to yourself by drawing a picture. If we do our tangent x and our secant x, and do our window negative pi over 3 to pi over 3. It's always good to visualize the region just so we can hopefully keep straight the, I'm going to go pi over 6 as my scale here. I don't need to go negative 5 to 5. So, as we suspected, there's our tangent. And then our, looks like there might be a convenient intersection point here at pi over 3. Possibly. Find out. But either way, whether there's an intersection point there or not, it really doesn't matter because it told us to use negative pi over 3 to pi over 3. So even if these didn't cross here, okay, we still have a top minus bottom situation. True? And so ultimately here in our picture, it says that in part A, that the circular disk with diameters running from the curve to the other curve. So let's just say for argument's sake that I use that as my slice right there. And I have circular disks again, so that's going to be kind of the same issue we had last time. We're going to have a disk created by that slice, if you will. And so we're going to find the area of that slice. Our area here is going to be pi r squared. And the r here is going to be, remember this, if I do secant minus tangent, that would give me the diameter. Okay. But ultimately we only want half of that, secant minus tangent. So that would ultimately be my equation for my area of said disk. Again, keeping in mind that the diameter is going to be the secant minus tangent here. That's going to be that distance between those two. Half of that is going to be the radius. And if we square everything here, we're going to get pi over 4 out in front, and then secant x minus tangent x all squared. All right. So with that, and if we want to find the volume here, which means we're going to sum up all of those circles that we're creating, take our pi over 4 out, and we'd be left with secant x minus tangent x all squared. Keeping in mind that secant x minus tangent x all squared is not a known derivative. Okay. So if we're going to do this analytically, which I believe it says we need to, right? Okay. The question is, can we do anything with this in terms of making it into a simpler function that might be easily anti-differentiable for us? Okay. Well, let's see. Let's take it over here. If we were to, let's say we multiply that out, we'd get secant squared x minus 2 secant x tangent x plus tangent squared x. Space here, but ultimately if we foiled that, if we wrote that twice and foiled it, we'd get that. True? Now remember one of our identities that we have here is that 1 plus tangent squared equals secant squared. So we could theoretically get rid of a secant squared with a 1 plus tangent squared. So let's see what happens if we do that. If we do 1 plus tangent squared x minus 2 secant x tangent x plus tangent x squared x, that is. We'd have that. And ultimately we'd have 2 tangent squared x. We'd have secant tangent, so on, which ultimately arguably doesn't really help a whole lot. So what if we did it the other way around? What if we replaced the tangent x with the secant squared minus 1? So if we did that, we'd have secant squared x minus 2 secant x tangent x. And if we replace that with secant squared x minus 1, now we would have 2 secant squared x minus 2 secant x tangent x minus 1. Alright, so question is, is that helpful? Well, if this is our integrand, keep in mind this is going to be our integrand if we choose this as the right way to go. Okay. What's the antiderivative of secant squared? It's tangent. And what's the antiderivative of secant tangent? It's secant. And the derivative of 1, of course, is just x. So in this form, we'd be able to have something we could anti-differentiate, wouldn't we? So ultimately, again, this one, we could not anti-differentiate. So ultimately, in our integrand, we'll write 2 secant squared x minus 2 secant x tangent x minus 1 dx. And from there, like I said, we can anti-differentiate now. We'll have our pi over 4 out here. We'll have 2 tangent x minus 2 secant x minus x, negative pi over 3 and pi over 3. Alright. And ultimately, like I said, the calculus part at this point is over. We just need to be able to put those numbers in there and do the trigonometry algebra part of getting the values here. So remember at pi over 3, keep in mind the values of tangent. We're at pi over 3, we're here. That means that we're at the point 1/2 radical 3 over 2. So if we did, this is cosine sine, remember? So if we do sine divided by cosine, tangent of pi over 3 is just going to be radical 3. So if I have pi over 4, we'd have 2 radical 3 for that part, minus the secant of pi over 3. Secant, remember, is 1 over cosine. This is our cosine. So 1 over 1/2 is going to be 2. So it'll be minus 2, and then minus pi over 3. So that would be our first part, if you will. And then minus, if we do the same thing with negative here, negative pi over 3 is going to be down here, which is going to be 1/2 negative radical 3 over 2. And so tangent is going to be negative radical 3. So we're going to have negative 2 radical 3, if you will, in those parentheses. Secant is going to be minus negative 2. Nope, I lied, minus 2. Remember, secant's 1 over cosine. Cosine's still positive here in the fourth quadrant, so this is still a minus 2, if you will. And then minus negative pi over 3. So we plus pi over 3 in there. Alright. So let's see if we can go to work here. We got still the pi over 4 on the outside. Simplifying, we have 2 radical 3 minus negative 2 radical 3. That'd be 4 radical 3. Negative 2 minus negative 2. Those would be gone. Negative pi over 3 minus pi over 3 would be negative 2 pi over 3. And with that, we'd have pi radical 3, I guess. We multiplied into here. And then we'd have minus pi squared over 6. 2 pi over 12, we multiply. So ultimately, again, the key issue here with the calculus part is that we can actually set up the integral correctly. In most cases, especially on the AP test, okay, if we're expected to set up an integral like this, as long as we have this integral set up like this, we wouldn't even probably even have to do most of this stuff. Okay, most of this is pre-calc stuff, basically. You know, we're finding those values and so on. Like I said, on the AP test, especially if this was on the calculator part, you would just set this up and put it in your calculator. Okay, and get a decimal answer for it. If it was on the non-calculator part, for the most part, I have not seen one that takes this much pre-calc work to get the answer to it on the AP test on the non-calculator part. It's usually going to be an integral that's going to be easier to anti-differentiate and evaluate. Okay. So this is a good problem, though, because it's a good test to make sure we can be careful with our trig identities and trig functions and so on. Okay. And the other one, I'll leave the second part up to you. Ultimately, you're just doing squares here instead of circles. So another good practice one, using secant, tangent, and so on. All right.